Welcome. Today is the last episode of the Discrete random variable series. Last time, we proved the Borel Cantelli lemma. It gives us conditions for a series of events to be happening infinitely many times. If the series of corresponding probabilities is convergent, the probability of infinitely many events happening in the series is 0. If it is divergent and the events are independent, that probability will be 1. There is something binary about the infinity. Either something happens with probability 1, or almost surely, as we should say, or it is impossible. Today we want to generate in R a series of events that will be happening infinitely many times according to Borel Cantelli lemma. We can't go as far as infinity because our computers are finite machines. Just like we had the smallest possible number of type double, which is called machine epsilon, we also have the biggest possible integer. To get this number, we type in dot machine $sign integer dot max. Let's see this number. It's of the order of 2 billion. In the first episode on the Borel Cantelli lemma, we used the for loop. If we try to do it here for k in 1 to maximum integer, do nothing. Let's see what happens. If we try to do it, R says that we get an error of allocation. Allocation of such vector would take 8 gigabytes. So let's use the while loop instead. While loop does not use the vector as for loop does, but we have to initiate our index at 1. So we write while k is smaller than maximum integer, do. So we want to generate events whose probability of success is decreasing, but probability series is divergent. Let's use probability equal to 1 over square root. This is the function to get a square root in R of k. We will use our old method to get successful Bernoulli trials with such probability by comparing random uniform number to this probability. We would like to see only the numbers corresponding to the successful trials. To do that, we will use if statement. If we get a successful trial, then this condition will become true. Then print our index k. We would like to see the results on the run. So we type in flash.console like we did last time. And finally, we need to increment the value of our index k, as the while loop will not do that for us. So we say k equals k plus 1. Okay, let's go. So what do we see here? At the beginning, the successes are very frequent. But the bigger our index k, the smaller the probability of success. The further we go, the longer we will have to wait, on average, for the next successful trial. However, thanks to Borel Cantelli lemma, we are confident that no matter how far we are, successful trials will keep on happening forever. Have you noticed some jumps like this one in the probability series? Couple of successful trials not far from each other? It could happen once or twice, but seems quite unlikely to recur if probability is very small. Why is that? Did we miscalculate something? We should see no cyclicality if these numbers are random. So maybe they are not random. After all, how can a computer, which is a binary machine, generate random numbers? It cannot toss a coin or roll a dice. It can only process strings of zeros and ones. So what is the source of randomness? Is there such thing as source of randomness? Or is our whole world deterministic? Can we change something in our lives? Or are all outcomes already determined by the chemical processes in our brains? We will explore answers to some of these questions in the next series about the continuous random variables. Now, I leave you with the loop.